Okay, Algebra 2, Unit 1, Lesson 9 of Illustrative Math is called What's the Equation? All right, so in this lesson, we're going to look to come up with an equation to represent a sequence. We're going to do a little bit with a recursive equation and an explicit equation. Okay, so our learning goal today is I can define a sequence recursively and explicitly. So just to make sure before we jump into the lesson, we understand what recursively and explicitly are. Recursively uses the previous term in the definition. Okay, so if I wanted to define it as like f of n, well, the term before the nth term would be the n minus 1 term. Okay, so I have to do something to the previous term. Okay, 3 times the term before. Okay, so think about this here. If I have the first term, the second term, third, and so forth, and then eventually I get to the nth term. Okay, the term before it is going to be one less. It's going to be n minus 1 term. Okay. You can kind of tell, like if I look here at these two, the term before the third term is one less. It's the second term. Okay. The term before the second term is the first term. It's one less. If I look at these two, okay, the term in front is always one more. That's just how you count. Explicitly is basically just going to use n to find any term. So the explicit formula is a little bit more functional when you get like big numbers. Like if I say find the 1,000th term, okay, that's a little bit more useful because you could just plug in the number 1,000 and it'll tell you exactly what it is. You don't have to like start at the first term and count up as you would with the recursive formula. So that's a little just a brief review of what those are. All right, so a little warm up here. So this is just a little review of order of operations, multiplying fractions, and function notation. So it says to evaluate mentally. I'm not going to use a calculator, but I will use some scratch work on the side. So f of 0. So what I'm going to do here is I'm going to plug in 0. Plug in 0 here for x, so it's going to be 32 times 3/4 to the 0 power. Okay. Now you got to do your order of operations first. So this here has to get done first. Exponents come before multiplying. So anything to the 0 power is 1. So this is going to be basically 32 times 1, which is just 32. Okay. So if I wanted to say 32 equals f of 0, that means the 0 term is 32. 32 times 3/4 to the first. And again, same idea here. You got to do this first. So 3/4 to the first is just 3/4. And then again, I'm not using a calculator, so I'm going to put this over 1. And then this 32 and the 4, I'm going to cancel these. So 4 goes into 32, I believe, 8 times. So now it's just 8 times 3, and 1 times 1 is just 1. So 24, and that equals f of 1. So that means the first term, f of 1, first term is 24. 32 times 3/4 to the second power. Okay, again, I do that exponent first, so it's going to be 32. And it's real easy. You can just square the numerator and square the denominator. So 3 squared is going to be 9, and 4 squared is 16. And then I'm going to put that over 1, and I'm going to reduce before I multiply. I could just multiply 32 times 9 and 1 times 16, but I realized that 16 goes into 32 twice, so I just get 2 times 9 is 18. All right, so f of 2 equals 18 means the second term is 18. Or it basically means when you plug in 2 for x, you get 18. All right, and then the last one, 32 times 3/4 cube. Again, we're going to cube the 3 and cube the 4. Now remember, 3 cubed is not 3 times 3. It's 3 times 3 times 3. And same thing with 4 cubed. It's 4 times 4 times 4. So just over 1. This time when I cancel the bigger numbers down here, the 2 is there and the 1 is there. So I get 27 over 2 equals up from 3. Okay, 27 over 2 is like, what's that, 13 and a half? Okay, so there's our warm up. All right, next thing, take the cake. A large cake is in a room. First person who comes in takes 1/3 of the cake. Then a second person takes 1/3 of what is left. Then a third person takes 1/3 of what is left, and so on. Complete the table for C of n, which is the fraction of the original cake left after n people take some. So this is where it gets a little tricky, because a lot of people think that C of n is you're just multiplying by 1/3, but it's actually you're multiplying by 2/3. So if I were to make a cake here and divide it into thirds, I'm going to do my best to do that. Okay. So we have the cake split into thirds there, roughly. If someone comes and takes 1/3 of it, okay, I'm just gonna erase this. This person takes this slice right here, and it's gone. Okay, how much is remaining would be 2/3. Okay, because if you look here, C of n is the fraction of the original cake left after n people take some. It's not how much they've taken. So go over to our table here. If no one's taken any cake, we have a whole cake. We have one full cake. Now, after one person has taken that slice right here, okay, that slice right here that kind of that person took, okay, we have 2/3 remaining. So how did I get there? Well, I times by 2/3. Okay, so then out of what remains here, okay, you're going to have 2/3 of that. Someone's going to take 1/3 of it, and you're going to have 2/3 remaining. So I don't know, this is a little harder to divide into thirds, but let's say here, I don't know, maybe cut this into thirds here. That looks, no, that's not good. Let me try that again, make it a little bigger. Something like that. Those look pretty equal. So someone comes and takes this piece out of here, so I'm just going to cross it off. All right, we have 2/3 of that left. So what you see here is you're going to keep multiplying by 2/3 each time. Okay, so you start with 2/3. So basically, to get to the next one, 2/3 times 2/3 is just going to be 2 times 2 is 4. 3 times 3 is 9. And then you can just keep multiplying the top by 2 and the bottom by 3. Top by 2, bottom by 3. Okay, so there's the first part. All right, write two definitions for C, one recursive and one non-recursive. So let's see here, one recursive and one non-recursive. I should have left a little bit more room here. So your recursive one is going to be pretty easy. What do you do to the previous term? Well, the previous term is C of n minus 1, and you keep timesing it by 1/3. Okay, C of n, you got to take, to find the nth term, you have to take the term before it, which is this C of n minus 1, and then you times it by 2/3. You do also want to make sure that you give the initial term. So our first term is right here. It's not C of 1, it's C of 0 is your first term. C of 0 equals 1. That way you know where you're starting at. And then you could count up to 12th term or the 50th term. It would just take you a long time, but you have a definition and you can do it. So that would be my recursive formula. Just put a little R here. Okay, and then my non-recursive formula. So what you notice here is you just basically keep multiplying by 2/3. Okay, so we start with 1, and we're basically, the only thing we're doing is multiplying by 2/3 over and over again. So what I'm going to do here for my explicit formula, so I'm going to say, to find the nth term, we're basically just going to take 2/3 to the nth power. Okay, and then I'm going to kind of check it here. I'm going to just say, oh, okay, what's C of 4? Does it work? 2/3 to the 4th, does that work? 2 to the 4th, 2 times 2 times 2 times 2 is 16. 3 to the 4th is 81. That works. Maybe double check another one. Try C of 3. 2/3 to the 3rd. 8 over 27. That works. Okay, so it checks out. You don't really need the first term there with the explicit because you could just plug in any number of n. You don't have to go in order. If I wanted to find the 7th term, I don't have to count up from 0. I can just plug in 7. All right, last thing. What's a reasonable domain for this function? So basically for n, and in this situation, so obviously you're not going to have negative people taking cake, because n represents, always important to go back and look, what does it represent? N represents the number of people that have taken cake. So n has to be greater than or equal to 0. Okay, but eventually, if you keep slicing the cake and taking cake away, you're going to kind of like run out of enough cake that you can slice. It'll kind of turn to crumbs. So I don't know, maybe like, depending on how big the cake is, I think after like, 9 or 10 cuts, you're gonna run out of cake to slice. So that question could have multiple correct answers. Okay, but there it is. Okay, so next thing on graph paper. Draw a square of side length 1. Draw another square of side length 1 that shares a side with the first square. Okay, so let's start here. Let's see here. Start with this. I'm going to go right down here. Okay. And then draw another square of side length 1 that shares a side with the first square. Okay, so I'm going to draw another one right here. Okay. So I've done that. Let's go to the next one. Next, add a 2 by 2 square with one side along the sides of both the first and the second. So let's go over here, 2 by 2 square. Next, add a square with one side that goes along the sides of the previous 2 squares. Okay, so I'm going to go up here. So this is 3. So it has to be the same length. It has to be a square. Okay. And then do it again. So I'm going to come over here where these 2 are on the right. How many is this? 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. Okay, cool. All right, so you should get something like that, depending on where you put your squares. Should look something along those lines. Okay, so write a sequence that lists the side lengths of the squares you drew. Okay, so this was my first square right here. So that one had a side length of 1. The next one was right there. That had a side length of 1. The third square was right here. So that had a side length of 2. the third square was right here. That had a side length of 3. And then the last one is this big one over here, and that had a side length of 5. All right, I'm guessing this pattern is going to continue, but you can kind of look here. First one, second one, third one, fourth, and so forth. Okay, we'll put another color in there. All right, there we go. All right, so there's my sequence. Go to number 3. Predict the next 2 terms in the sequence and draw the corresponding squares to check your prediction. So I'm not going to look at the picture. I'm going to just kind of go to the sequence there. And it might be hard for you to notice, but what happens is if I want to find this third term, I take these 2 here and add them together. 1 plus 1 would give me 2. Okay. All right. And then if I wanted to find this term here, okay, I'd have to add these 2 together to get that. 1 plus 2 would give me 3. Okay. So the next term would be these 2 added together. That would give me 8. And then I would take, basically, there was a 5 in front of that. So then I'd take these 2 and add them together, and I get 13. And that's all they said, the next 2 terms. So we're good. So I'm going to erase that 5, because I just use it to help me. All right, and then I'm going to check my work here. So I'm going to come up here. This side here has 1, 2, 3, 4, 5, 6, 7, 8. So I got to go up 1, 2, 3, 4, 5, 6, 7. I have just enough graph room here. Okay. And then the next one is going to be 13. So I go 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13. All right, so it looks like it checks out. And then I go down here. Number 4, describe how each square's side length depends on the previous side. Well, you can clearly see that you're adding, like for here with that one, you can see that you're adding these 2 sides together. Okay, so let's say we're adding the previous 2 sides to construct the new side. Okay. And then the last thing, let f of n be the side length of the nth square. So f of 1 is 1, and f of 2 is 1. Write a recursive definition for f. Okay, so if I want to find the nth term, I need to take the 2 terms before it. Okay, so if the nth term is here, I'm going to count backwards. This is going to be the n minus 1, and that's going to be the n minus 2. So I'm going to have to take f of n minus 2 and add that to f of n minus 1. And that'll give me the nth term. And then we should also put here f of 1 equals 1. That way we know where we're starting. Okay? Oh, and I guess we should also put f of, they told us this, but 2 equals 1 as well. So that's, that way we know where we start. Okay? And we can count up as far as we want. All right, lesson synthesis. Pattern represents a sequence where sequence W, where W of n is the number of white circles in step n. Okay, so if I look here, I have 4. If I look here, I have 7. If I look here, I have, what do I have here? 4, 8, 10. Okay, so it looks like I just keep adding 3. All right, so let's write an explicit formula here and recursive. The recursive is easy. If I wanted to find the nth term, all you do is you take the term before it and you add 3. Okay, we need to know where we start though, so we're going to say W of 1 equals 4. Okay, so we know our first term that we start at 4, and then we keep adding 3 to find the next term. We keep counting up. Okay. My explicit formula is going to be a little bit harder. So if I want to find the nth term, what we have to do is we have to use our step number for n. Okay, so what we need to do is we need to somehow take a look at this and see if we can figure out a way to come up with that. Now, you keep adding multiples of 3, okay? So think about it, 3 times n, would that work? Well, no, because if this first step I plug in 1, that's not going to work. But what if I started with 4, I start with 4, and then I do 3 times n minus 1. So that way, like the first step, like if I want to find w of 1, and I'm going to kind of check this, it's going to be 4 plus 3 times 1 minus 1. So this is 0, so I'm not adding anything here. It's really just going to be 4. That works. Step 1 over here is 4, okay? So that works. All right, let's try the next one here. W of 2, it would be 4 plus 3 times, that's step 2 minus 1. So it's really going to be 4 plus, so 2 minus 1 is 1, so it's 4 plus 3, which gives me 7. So W of 2 equals 7. That works. Okay, so what ends up happening is, I'm going to erase all of this here. What ends up happening is you have to subtract 1 because that first step is where you're starting. You haven't added 3 at all. You don't add 3 until you get to the second step. So there's got to be 1 less than the step number. Okay? Oops, I had that slide twice. All right, cool down. So here are 2 definitions of the same sequence. Definition 1 looks like it's recursive because you have that f of n minus 1. Definition 2 is explicit because although you have the n minus 1, it's not f of n minus 1. So it's still it's still just an explicit function where you could plug in n. Okay, so that's the first 4 terms of this sequence. So you could really use either one. We know the first term is 64. If I look at this definition, it looks like to find the next term, I just take the previous term and times it by 1/2. So I could just kind of count it out right here. I'm just going to keep on going. If I wanted to use the explicit, okay, I could say, oh, okay, well, f of 1 equals 64 times 1/2 to the 1 minus 1. And you know, when you plug this in on your calculator, make sure you put that exponent in parentheses, or you just mentally do the math. But it's going to be 64 times 1/2 to the 0. Anything to 0 is 1. That's how I get the 64. Okay. And then I could plug it in again. I could find f of 2. I could do 64 times 1/2 to the 2 minus 1, which ends up just being 64 times 1/2, which gives me the 32. You can plug them all in. And you might say, why would I want to plug them all in when I could just count? You know, it just depends on the question. If I asked you find the 80th term, you wouldn't want to count. Okay. So like look at the second one. Write an expression to represent f of 20. I don't want to count out to the 20th term. I'm going to just use definition 2, which is my explicit formula here. I'm going to say f of 20 equals 64 times 1/2 to the 20 minus 1 power, which I'll tell you what, I'm gonna just erase the 20 minus 1 and make it 19. Okay, there's an expression. Could I go ahead and calculate that? Sure, it didn't say that I have to, so I'm just gonna leave it. All right, number 3. Person is trying to quit chewing gum. They decide they'll have 64 pieces in week 1, but each week have half as many as the week before. Kind of looks like our situation here. Function f represents the number of pieces of gum they will have in week n. What is a reasonable domain for this function? Explain your reasoning. So n has to be greater than or equal to 2, because week 1 they start with 64 pieces, so we're not going to plug in 1. So it would have to be greater. Well, I guess you could. I guess we're starting at week 1, so I guess we could start there. I guess we could plug in 1 and get 64. So n would have to be greater than or equal to 1. Eventually, you're going to run out of gum, run out of pieces. You're not going to be having, half a piece of gum or a fraction of a piece of gum. So eventually, you start getting anything. I think if you plug in 7 might be a number that's less than 1. If I plugged in 64 times 1/2 to the 7 minus 1. Plug that into your calculator. I think that number is less than 1, so that wouldn't make sense. You wouldn't have less than 1 piece of gum in a week. So I'm going to say we're going to do less than or equal to 7 for my domain. All right. All right. Well, hopefully you guys enjoyed this lesson, and that's it.